Section: Introduction. In this section, we discuss diffusion models, which have made significant progress in generating high-quality images and videos. However, when we use basic sampling methods, the quality of the generated samples can be less than ideal. One effective technique, known as classifier-free guidance, enhances the chances of a sample belonging to a specific class by adjusting the scores from conditional and unconditional models. While this method is useful, it requires extra training and can lead to lower sample quality if the guidance scale is too high. We have seen various guidance sampling methods emerge, including the concept of weak models, where we intentionally weaken a model to assist a stronger original model. Although these approaches generally improve performance, they have limitations. For instance, auto-guidance relies on a poorly trained unconditional model, which can be difficult and unstable to train. Other methods, like perturbed attention guidance and smooth energy guidance, modify attention mechanisms but introduce additional parameters that need careful tuning. All current guidance sampling methods require extra evaluations of neural functions and cannot be used with guidance-distilled models because they need to calculate differences between models. This presents an interesting challenge. Can we create a universal boosting method that avoids extra training or evaluations, works with other guidance methods, and is applicable to guidance-distilled models? To address this challenge, we explore attention-based methods from a new perspective. A key contribution of our work is recognizing the value of sparse attention, particularly through a technique called alpha entmax, which includes softmax as a special case. Sparse attention has been well studied in natural language processing but not extensively in computer vision, especially in diffusion models. Our findings show that replacing cross-attention with sparse attention during inference significantly enhances generation performance. This approach avoids the need for additional inference time and remains compatible with other guidance methods. We also relate our results to modern Hopfield networks, where the attention layer mimics the update rules of these networks. Using sparse attention offers noise robustness, supporting our approach in diffusion models. Based on these insights, we introduce a straightforward method called PLADIS, which assigns weights to the differences between sparse and dense attention to highlight sparsity. Our method effectively addresses the challenges we identified, leading to better performance and improved text-image alignment, as shown in our experiments. Our main contributions include proposing PLADIS, which replaces cross-attention in diffusion models with adjusted attention mechanisms that balance between sparse and dense attention. We provide a thorough theoretical analysis based on sparse Hopfield networks, including error bounds and noise robustness for intermediate sparsity. To our knowledge, this is the first study to enhance diffusion models from the perspective of sparse Hopfield networks. Our method can be combined with other guidance techniques and does not require additional training or evaluations. We demonstrate these advantages across various benchmark datasets, showing significant improvements in image quality, text-image alignment, and user preference evaluations. Now, we will delve into the details of diffusion models. These models are designed to learn the reverse of a noise process by utilizing the score function of the data distribution. The forward process adds noise to the data in a series of steps, creating a distribution of latent variables that approximates a Gaussian distribution. The reverse process is modeled to generate samples from this distribution, and we can train the model using different objectives, including denoising score matching. The sampling process begins from a Gaussian distribution and iteratively refines the samples. Section Summary. In this section, we discuss the advancements in diffusion models for generating high-quality images and videos, highlighting the limitations of existing guidance methods that require additional training and neural function evaluations. We propose a novel approach, PLADIS, which utilizes sparse attention mechanisms to enhance performance without extra training or inference time, demonstrating significant improvements in sample quality and text-image alignment. Section: Guidance sampling in diffusion models. In this section, we discuss how to generate samples based on user-defined conditions by extending diffusion models into conditional generative models. Here, we sample variables in a similar way as before, with a specific condition represented by an embedding of a class or text. However, Standard sampling often yields poor results for conditional generation, prompting us to explore various guidance sampling methods to improve sample quality. To simplify our notation, we define a function that represents the conditional model and denote the unconditional model with a null condition. Classifier-free guidance modifies the probability of the class-conditioned output in relation to the unconditional output, leading to an adjusted sampling process influenced by a guidance scale. Recently, a weak model guidance approach has emerged, which intentionally weakens the conditional model and calculates the difference from the normal output. This method uses various techniques to perturb the model, such as altering attention weights or noise levels. While these methods are effective, they have drawbacks. They require specific layers to be identified, increase computational costs, and are not compatible with certain models. Our approach addresses these limitations. Next, we explore energy-based interpretations of attention mechanisms, which have gained traction in various fields, including diffusion models. By viewing attention through the lens of energy-based models, we can relate them to Hopfield energy functions. In Hopfield networks, we aim to connect an input with the most relevant pattern by minimizing an energy function through retrieval dynamics. Modern Hopfield networks have proposed energy functions that align with attention mechanisms, providing a theoretical foundation for their effectiveness. We also introduce the sparse Hopfield network, SHN, which modifies the energy function to enhance the efficiency of retrieval dynamics. This involves controlling the sparsity of the probability mapping, where a specific parameter adjusts how sparse the outputs are. As we increase this parameter, the outputs become sparser, which can improve retrieval accuracy and speed compared to dense retrieval dynamics. Furthermore, we highlight the noise robustness of the sparse Hopfield network. We present a theorem indicating that when dealing with noisy patterns, the impact of noise on sparse retrieval errors is linear, while it is exponential for dense retrieval errors. This suggests that under noisy conditions, sparse attention mechanisms are more robust and lead to lower retrieval errors compared to standard dense attention. Section Summary. In this section, we explore how diffusion models can be enhanced for conditional generation through guidance sampling methods, which improve sample quality by adjusting class condition probabilities relative to unconditional ones. We also discuss the connection between attention mechanisms and energy-based models, highlighting the advantages of sparse Hopfield networks in terms of noise robustness and retrieval efficiency compared to dense networks. Section. Main Contribution, PLADIS. In this section, we focus on our main contribution, PLADIS. Building on the benefits of sparse attention discussed earlier, we set out to improve text-to-image, T2I, diffusion models by incorporating sparse attention modules, as outlined in our sparse-atten approach. We will examine the role of sparse attention in both self and cross-attention for T2I diffusion models, analyze how sparsity affects the alpha entmax function for values greater than 1, and connect the noise robustness of the SHN model with sparse attention for alpha values between 1 and 2. Ultimately, we will present PLADIS as a cost-effective enhancement for T2I diffusion models. To evaluate the effectiveness of the sparse attention mechanism in T2I diffusion models, we first replace the standard self-attention and cross-attention modules with their sparse versions using the alpha entmax function. When we substitute the self-attention modules, the model fails to produce meaningful outputs. Sparse attention helps to disregard irrelevant correlations while keeping the important ones intact. However, in self-attention, the strict relationships between noisy image patches lead to poor results. Interestingly, when we replace the cross-attention module with its sparse version, we observe improved generation quality and better alignment with the text, even though the model was not specifically trained with these sparse modules. Our baseline results struggle to generate the text boost, while the sparse variants succeed in producing accurate text. This notable finding regarding sparse cross-attention in T2I diffusion models motivates our proposed algorithm. Next, we investigate the impact of sparsity in the cross-attention module of T2I diffusion models. We control sparsity using the alpha parameter, where alpha equals 1 corresponds to softmax and alpha equals 2 refers to a different function. The alpha and max transforms are sparse for all alpha values greater than 1. To evaluate the effect of sparsity, we replace standard cross-attention layers with sparse ones and generate 5,000 samples from the MS-COCO validation dataset, varying alpha. We find that increasing sparsity, or higher alpha values, enhances generation quality, text alignment, and human preference scores without requiring additional training. While cross-attention with softmax results in dense alignments and strictly positive output probabilities, sparse cross-attention yields sparser alignments, ensuring a more precise match between image and text embeddings, leading to overall performance improvements. To further understand why performance improves when alpha is between 1 and 2, we introduce the concept of retrieval error dynamics for this range. We denote the retrieval dynamics of the Hopfield model with alpha and max as T_alpha. We derive a polynomial relationship for the impact of noise on retrieval error when dealing with noisy patterns. This suggests that T_alpha exhibits noise robustness for alpha values between 1 and 2, resulting in lower retrieval errors. In T2I diffusion models, cross-attention layers handle query, key, and value matrices derived from noisy images and text prompts. Given the Gaussian noise present in the diffusion process, the query matrix is inherently affected. Our findings, supported by theoretical guarantees, indicate that the observed performance improvements, particularly with increasing alpha, reflect the noise robustness of sparse attention. This connection strengthens the case for the effectiveness of sparse cross-attention in diffusion models. Section Summary. In this section, we introduce PLADIS, a method that enhances text-to-image diffusion models by implementing sparse attention mechanisms, particularly in cross-attention modules, which significantly improve generation quality and text alignment without additional training. We also demonstrate that increasing sparsity, controlled by the parameter alpha, enhances noise robustness and overall performance in the presence of Gaussian noise during the diffusion process. Section. Our approach, PLADIS. In this section, we introduce our approach called PLADIS, which builds on our investigation of sparse attention. Our goal is to enhance the advantages of sparse attention without adding extra neural function evaluations. We draw inspiration from various guidance methods and extend query-key correlations in both dense and sparse attention settings. The scale parameter, which we refer to as lambda, determines how much we amplify the effects of sparse attention. When lambda is 0, we revert to the baseline model. When it is 1, we align with the specific model discussed earlier. For values greater than 1, we apply PLADIS. We also consider the sparsity degree, represented by alpha, focusing on two specific values, 1.5 and 2, where efficient algorithms are available. We highlight that our method is generalizable. Unlike other methods that require parameter searches for specific layers, PLADIS can be applied to all cross-attention layers, making it easier to extend to other scenarios. Our ablation study confirms that applying it to all layers yields the best results. Additionally, our method is implicit, meaning it doesn't need an extra model, allowing it to be used with guidance-distilled models. For our experiments, we utilize Stable Diffusion XL as the backbone model to test the effectiveness of our methods, with results from other models available in the supplement. All experiments are run on a single NVIDIA H100 GPU, and we use an open-source library for calculating the alpha and max function, setting alpha to 1.5 and lambda to 2 as our baseline. To evaluate our method comprehensively, we employ various metrics. We calculate the Frechet inception distance for images generated from 30,000 random prompts from the MS-COCO validation set. We also assess text-image alignment and user preference using clip score, image reward, pick score, and human preference score. Our model is tested with prompts from MS-COCO, Drawbench, HPD, and Pick, with more details in the supplement. In our results, we generate 30,000 samples with and without guidance sampling techniques. We find that using PLADIS without additional guidance significantly improves visual quality, text alignment, and user preference. Our method works well with different guidance approaches, providing meaningful enhancements when combined with weak model guidance. Our experiments on a human preference dataset show that PLADIS consistently outperforms other methods across all metrics and guidance techniques, leading to more visually appealing outputs and better text-image coherence. We also explore how our method can help surface previously latent concepts. Our analysis indicates that the baseline model struggles to generate certain concepts, but with modified inference steps, we can enable the model to utilize its existing knowledge effectively. To further validate PLADIS on guidance-distilled models, we conduct experiments with various baselines using 4-step sampling across different datasets. Our method significantly boosts performance, especially in text alignment and human preference, compared to state-of-the-art methods. We observe improvements in visual quality and performance even with 1-step sampling. Lastly, we assess user preference by having evaluators compare outputs from models with and without PLADIS. The results show that all models incorporating our method outperform those without it in both image quality and prompt alignment, particularly enhancing prompt coherence. Further details of this user preference study are available in the supplement. Section Summary. In this section, we introduce PLADIS, a method that enhances sparse attention without requiring additional neural function evaluations, allowing for easier application across all cross-attention layers. Our experiments demonstrate that PLADIS significantly improves visual quality, text alignment, and user preference in generated samples, outperforming existing guidance methods and distilled models. Section: Ablation Study and Analysis. In this section, we explore the effects of the parameter alpha by adjusting its value in alpha entmax, as illustrated in our figures and tables. We generate 5,000 samples using guidance from the MS-COCO dataset. When alpha equals 1, we are using the baseline sampling with the softmax operation. For values of alpha greater than 1, we replace the cross-attention mechanism with the corresponding operation in alpha entmax. We consistently find that adding sparsity to cross-attention improves performance for alpha values above 1, which aligns with our theoretical insights on the noise robustness of sparse attention in diffusion. In our study, we consider alpha values like 1.5 and 2. Our approach with alpha set to 2 yields the best results in terms of FID and clip score, although it performs worse for image reward. The alpha value of 1.5 provides balanced improvements across all metrics, making it our default setting. To assess the efficiency of PLADIS, we compare inference time and memory usage in VLAM by varying alpha. Unlike other guidance methods, our PLADIS does not require additional inference at each time step, although it does involve systematic calculations of alpha entmax. We observe that our method achieves the best performance while only slightly increasing processing time per prompt to 0.56 seconds and memory usage to 0.01 gigabytes compared to the baseline. Notably, our default setting of alpha equal to 1.5 is about 3 times faster than other alpha values, except for alpha equal to 2, and shows minimal differences compared to alpha equal to 1.5 without PLADIS. The scale lambda controls how much sparse attention with alpha entmax differs from dense attention. A higher scale enhances the effect of sparse attention during denoising. In our experiments, we sample 5,000 images with scales ranging from 1.0 to 3.0, evaluating results using FID, clip score, and pic score. We find peak performance at a scale of 2.0 for FID and clip score, and at 1.5 for pic score. Increasing lambda improves visual quality and text alignment, leading us to set the default configuration to lambda equal to 2.0. In addition to alpha and lambda, we can adjust beta, which corresponds to alpha entmax with different features. We discover that our method can be extended to various beta values. While we have conducted experiments under diverse conditions and with different backbone models, we have not yet applied our approach to more complex architectures like the multimodal diffusion transformer used in Stable Diffusion 3 and the Flux model. Our experiments have also been limited to text-to-image generation tasks. However, we believe that PLADIS can be adapted for other tasks, such as text-to-video or multimodal and language generation, and we plan to focus on these applications in our future work.